Up to this point, we've dealt with descriptive statistics, methods of organizing, summarizing our data. But as we move forward with statistics, we are going to move into something called inferential statistics. This is where we don't have access to the entire population of data, so we have to use samples to help draw conclusions about populations. And because it involves using information from just part of it to draw these conclusions, we can never really be certain that our conclusions are correct. This uncertainty is inherent in inferential statistics. And what Chapter 4 allows us to do is become familiar with uncertainty. The science of uncertainty is simply called probability theory. It enables us to evaluate and control the likelihood that a statistical inference is correct. So this particular chapter will help us understand the basics of probability theory. We see probability all the time. What's the chance something's going to happen? One of the biggest places, of course, go to a casino. Every game in a casino is based on probability. What's the chance that you are going to pull the lever on the slot machine and get a winning combination? What's the chance that you're going to roll a die and get a certain number before you get a 7 in craps? What's the chance that you drop a ball on a roulette wheel and it comes up either the winning color that you selected, or if you're really like to gamble, the specific winning number you selected? We see probability used quite often. So throughout this video, we're going to go through, of course, we're going to go through the specific formulas, but also when it comes to probability, I want you to think intuitively as well. Often, the formulas confuse things a little bit, in my mind, anyway. And if you even dare look at your formula sheet for Chapter 4, you're going to see a lot of formulas that can appear very confusing. Very often, you can kind of think through it intuitively before even looking at the formula. But let's start with the basic, the probability for equally likely outcomes. So let's suppose an experiment has n possible outcomes. So this uppercase N is going to represent what it always represents, the total number of our population. And all are equally likely to occur. An event that can occur in f ways has a probability of f over n. F represents the number of ways the event can occur, and n represents the total number of possible outcomes. So the first way we're going to look at probability is something you're familiar with when we worked on frequency tables back in Chapter 3. So let's suppose we have this table represents the female cardiovascular hospitalization over 1 year in Florida. So one particular year in Florida, over the course of that year, there were 810 females that had to go to the hospital for some sort of heart-related event who were between ages 19 or younger. There were 5,029 between ages 20 and 39. There were 10,977 between ages 40 and 49, and so on and so on. So we can use frequency tables to help us determine probability. So let's suppose that a woman is selected at random. That means each person has an equal likely chance of being selected. So the person is selected, a woman is selected at random. What is the probability that this person is in her 50s? Well, or less than 50, or between 40 and 69 inclusive, or 70 years or older. So I want you to stop and think about this. In order to do this, we need to have, of course, our F, which represents the total. Well, we have that. We have our F in her 50s. So 50 to 59, we know there were 20,983. But to get the probability, we need the total number. We don't have that as of yet. So there's a couple ways you can do that. You can just answer these questions, or you can go ahead and complete what we call a probability distribution. So what you can do is hit pause, get the total, and find the probabilities that are asked for here. So hit pause for a second and do that. Now, I went ahead and just calculated all the probabilities, and I got a total to be 208,867. So, probability that they are in their 50s would be the 20,983 divided by that total. And if you work that out, you will get 0.100461. Probability will always be between 0 and 1. If you ever get a probability less than 0 or greater than 1, you are definitely doing something wrong. So you got to change that. Now, let's look at this one, less than 50. So less than 50 means I'm going to use this group of numbers. So using the basic rule for probability, if I add those three up, I get 16,816 is my F, and I still have my total N. And when I divide them, I get the 0.0805. Now, as we progress through this chapter, you'll learn other rules where another way we could find that is also by adding up their individual probabilities. And you could see that would also come out to 0.0805. So between 40 and 69. Well, between 40 and 69, inclusive. So inclusive means we're including the numbers 40 and we're including the number 69. So it's going to be this particular group of people. So go ahead, calculate C and D on your own. And for between 40 and 69 inclusive, I got 0.329, approximately 70 or older, I got 0.642. So this is just using the basic formula for probability. Because this is a complete distribution, and we'll see these distributions in the beginning of chapter 5, one thing I want to note, we've covered every possibility for a woman with a cardiovascular event. They're either from 0 or over 80. Every possible age group is covered. Because of that, when you add up, if you have a complete distribution, if you add up all those probabilities and you can check it, you will get 1. Now, let's talk a little bit more about some of the probabilities we are going to see throughout chapter 4. And one of the basic things we can do is roll a die. Okay? Six-sided, basic six-sided die. What's the probability of getting a 3 when you roll a die? Well, of course, how many 3s are there when you roll a die? There's only one of them out of a total 6. When we work with probability, we like to put it over as a decimal, so let's take it 4 decimal places, 0.1667. How about the probability of getting an odd number? Well, we have 1, 3, 5 on a die that are odd, so that means there are 3 out of our total 6. That would make sense. You got a 50% chance of getting an odd number when you roll a die. So what about a probability of a number between 1 and 6, inclusive, meaning including 1 and 6 itself? Well, of course, isn't that every possible outcome that exists? We would get, there are 6 numbers out of the 6, and our probability is simply equal to 1. And then on the other end of that, what's the probability of getting a 7? Well, if you have a 6-numbered die, you can't get a 7. There are 0 out of 6, so our probability is 0. So let's change this up a little bit and say, what's the probability of getting a sum of 7 when you roll a pair of dice? So that makes it a little bit more difficult. You have to understand what our sample space is. When we rolled a single dice, our sample space was easy. Our sample space is every possible outcome. Well, you can get a 1, a 2, a 3, a 4, a 5, a 6. That is also our n. That's where we got n is 6 because there were 6 possible outcomes. Now, when you roll a pair of die, there's a lot more outcomes. You have to know how many outcomes exist. That's your sample space. N represents the size of that sample space. So you can stop and think for a minute, hit pause, and think about how large is your sample space when you roll a pair of die. Well, here it is for you. This is every possible combination when you roll a pair of die. All right? The red represents your first die and the black one represents your second die. So of course, if your first one's a 1, you can get a 1, 2, 3, 4, 5, 6. If your first die is a 2, you can get a 1, 2, 3, 4, 5, 6. So it's basically a 6 by 6 sample space. And the sample space, the n, is 36. So the question is, what is the probability of getting a sum of a 7? So let's think about this. How many come out to 7? Well, if you kind of understand what's going on here, I want you to notice something. This is the only one that has a sum of 2. There's the only one that has a sum of 12. Now take a look. 1, 2, 2, 1. These two have sums of 3. These 3 have sums of 4. So how can you get a 7? Well, it would be this one, right? 3, 4, 4, 3, 5, 2, 6, 1. 1, 2, 3, 4, 5, 6. There are 6 ways of getting a 7. Sorry, I don't know why I wrote the 7. There are 6 ways, right? 6, 1, 1, 6, 2, 5, 5, 2, 3, 4, and 4, 3. Out of 36, you have a 1 in 6 chance, which is 1, 6, 6, 7. 7 is actually the most likely sum when rolling a pair of die. The next sum that has a chance of happening is a 6 or an 8. They both have 5 ways that they can occur. So this is why the game of craps is, of course, built around the number 7. So please be careful when you're reading these probability problems. Are they asking you to roll a single die or a pair of die? And understand your sample space when you do this. Now, this leads us into experimental probability versus theoretical probability. So let's think about this a minute. If I asked you, hey, what's the probability of getting a tail when you flip a coin? Well, a tail, right, is 1 chance out of 2. You get a 50% chance of getting a tail. We can do that without flipping any coin. All right? Now, but again, what if I worded a little differently and said, how many tails do you expect to get when you flip a coin 10 times? That's still, we can still do this without going through the experiment. We would expect half the time to get a tail, so it would be 5 out. It's still good 50%. But now, if I asked, go ahead and flip a coin 10 times. Well, when you do that, some of you are going to get 2, some of you are going to get 3, most of you will get 4 or 5 or 6 tails during those 10 times, and I guess in the rare chance you could get 1 or all 10 of them tails, but you're most likely to get somewhere around 5 tails. The act of actually doing it is your experiment. That's experimental probability. The thinking about what you would expect to get is your theoretical probability. So this 0.5 is theoretical. But if you go ahead and perform the experiment and everyone does it, everybody's going to get it. Some of you will get 0.5, some will get 0.4, some will get 0.6. You'll get different numbers. So here's another idea. Your experimental probability, let's suppose you only flip the coin 10 times, and then let's suppose you go ahead and flip it 100 times. Which of those experiments do you think will get closer to the 0.5? What if we flip it 1,000 times? Okay, so here's a little simulation. If you flip a coin 10 times, so this is proportion of heads, same idea, it's still going to be 0.5. So the first time you flip a coin, you either got the heads or you didn't. So in this time, the first time they flipped it, they actually got it, so it was a 1. All right. When they flipped it 10 times, in this simulation, it looks like it came to almost 0.4. 10 times in this simulation was 0.6. But notice what happens on both simulations the more times you flip the coin. Your experimental probability gets a lot closer to that theoretical probability of 0.5. Now, so dice, coins, these are all concepts that we use a lot to help introduce probability. But one of the big things we like to use, and you'll see a lot of problems, is your standard deck of cards. So if you're not familiar with a standard deck of cards, I have a slide here. I'm trying to think. I think there's a picture of it in your textbook on page like 167, something like that. But know a standard deck of cards. All right, you've got the 4 suits, the hearts, the clubs, the diamonds, the spades. The hearts and diamonds are, of course, red. The clubs and spades are black. Each suit contains an ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this particular picture left out the, I'm just noticing that when I brought the picture over, it left out the, so you also have then a jack, you have a queen, and then you have a king. All right. The jack, the queen, and the king are all considered face cards. So there are 3 face cards in each suit. 13 cards altogether. So 1, 2, 3, 10, 11, 12, 13. You have a jack, a queen, and king. These are your face. Okay? So let's just recap some of these basics. Probability of an event is always between 0 and 1. It could be 0 if that event simply can't occur, like rolling a 7 when you roll 1 die. Or if the probability must occur, no matter what, in other words, getting a number between 1 and 6 inclusively, that's called a certain event, and that must occur. So let's talk about events. We already discussed sample space, the collection of all possible outcomes, and the event is the collection of outcomes for the experiment. That is any subset of your sample space. An event occurs if and only if the outcome of the experiment is a member. Basically, it's the outcome you want. Sorry about that. So here's a little Venn diagram showing you what can happen with an event. You have event E. This is everything that's in event E. So, for example, an event can represent, suppose an event, here your event can be your entire deck of cards. So you either got your entire deck of cards or you don't have your entire, it's not something in your deck of cards. But event A can be, I don't know, all 7s. And event B can be all red cards. Okay? So, if event A is all 7s, and event B is all red cards, then obviously there's some overlap, because 2 of those 7s are also red. So your 7 of hearts and your 7 of diamonds are going to occur in this space. Your 2 7s that aren't reds are going to occur here, and every other red card that's not a 7 is going to occur out here. If we were talking about pulling a card that is a 7 and also red. Now, 7 or red, you're still going to have that overlap in the middle, but we're going to include also all the 7s and all the reds when we use the word or. Or means everything, and means only if it has those exact attributes. 7 and a red card. 7 or red card means, yeah, then we're going to include the 7 of clubs and the 7 of spades. Okay, so again, that just kind of summarizes your relationship among events. Not E means the event does not occur. A and B, they both occur, and A or B, either of them occur. So this leads us into what we call mutually exclusive events. Two events are mutually exclusive if no two of them have outcomes in common. Okay, so let's talk about maybe this idea of event A is that the card in your hand is a heart. And then event B is the card in your hand is also a face card. So can those two events have something in common? In other words, is there a heart that's also a face card? Absolutely. A and B would fall into this category and are not mutually exclusive. So now I want you to look at these events, A, B, C, D, E, E, and come up with a pair that is mutually exclusive. Can you pick a pair of events in this list that have nothing in common? So sure you can. How about ace and face card? Remember, a face card is a jack, queen, king. If you do event B and event C, they are mutually exclusive because they don't have anything in common. You cannot pick a card that has these both attributes. Same as C and D, D and E, C and E. These are all mutually exclusive. What about B and E? What do you think of that? Well, of course, that is not mutually exclusive because E could be a jack and a face card could also be a jack. So try to understand this idea of whether two events are mutually exclusive. When you're dealing with more than two events, sorry, there's a lot of wind outside if you hear that in the background. When you're talking about more than two events, you can either have 3 mutually exclusive events, so that means of those 3 events, nothing is in common. But if they're non-mutually exclusive, B and C both represent non-mutually exclusive events. As long as one pair has something in common, then the whole group is not mutually exclusive. It doesn't have to be all 3 of them have something in common. If you're comparing 3 events, as long as 2 of them have something in common, they are not mutually exclusive. So, we're going to continue this video with some rules of probability, and then we'll end it before the next one. Some basic rules. First, the complementation rule. For any event, the probability of an event is 1 minus the probability of that event not happening. Sometimes it's easier to calculate the probability of an event not happening and then just simply subtract from 1. Sorry. Now, let's talk about the special addition rule. And this is where if you look at your formula sheet, I had talked about there's so many formulas on there. And, you know, you do have to understand how to use the formula, but you can also think through these problems intuitively without using the formula. And we'll do both here. So let's talk about the addition rule. Let's suppose we wanted the probability of A or B occurring. Well, the special addition rule says as long as they are mutually exclusive, meaning they don't have anything in common, you simply add up their two probabilities. So let's talk about a spade or a heart. Well, spades and hearts don't have anything in common, right? So we can simply figure out, well, what's the probability of a spade plus what's the probability of a heart? So, probability of a spade, well, as I said, there's 13 out of a deck of cards. That's 13 out of 52. Well, there's also 13 hearts, so that's another 13 out of 52. If you remember how to add your fractions, common denominator, just add up the numerator. And 26 out of 52 is 0.5. There, we just used the special addition rule for mutually exclusive events. But obviously, you could think through this. Well, I've got 13 spades and I have 13 hearts. I'm just going to add them together. That's half a deck of cards, so the answer is 0.5. But I want to change that now. What if we did a spade or a 7? Can we simply just add the spade, probability of spade, and add that to the probability of 7? What's wrong here? Well, number one, remember, special addition rule only works if they are mutually exclusive. Are spade and 7 mutually exclusive? No, because there is a card that is both. So then you think, all right, I can add up all the spades, right? And I can add up the rest of the 7s knowing that one of those spades was one of my 7s. This leads us to the general addition rule, where yes, and this is for any two events. Remember, if they're mutually exclusive, this applies for them as well. Just take the probability of the first, add it to the probability of the second, but now you need to take away what is in common. And what's nice about this is, well, if they're mutually exclusive, you're not taking anything away because there is nothing in common. So again, I could do probability of spade plus probability of 7 minus probability of spade and 7. All right, so yep, this spades, there's 13 out of 52 spades. There's 4 7s, right? How many cards represent a spade and a 7? 1. There was 1 overlap. So we have the 13 plus the 4 is going to give us 17. Subtract the 1. It's 16 out of 52. Intuitively, did you have to use the formula? Not necessarily. You could have kind of thought it through like this. Well, there's 13 spades, but one of them happens to be a 7, so that one's already counted. I then have to add to that 13, oh, the 7 of hearts, the 7 of clubs, and the 7 of diamonds. I got to add 3 more, and that gives me my 16 out of 52. Okay? So what I'd like you to do now is hit pause, and I want you to go through these events. Event A, the card is selected is a spade. B, it's a face card. Remember, that's your jack, queens, kings for each suit. C, it's red. D, it's a 5. E, it's a queen. So hit pause, and I want you to find those 7 probabilities I have listed. When you turn it back on, I will pop them on the screen. So I left the answers in the full fraction so that you can see them. Take a look. see how you did. Obviously, we can reduce these, we can get the decimal versions of these, but I'm just going to leave them in the full fraction right now so you can see how I did it and make sure you got everything correct. Obviously, B and C, face card and red. Well, there are 12 face cards, but only 6 of them are red, so that's 6 out of 52. There are 6 red face cards. So when we do B or C, well, we know we've got the 12 face cards, right? 3 in each suit. 3 times 4 is 12. We've got 26 red cards. That's half the deck. But we need to take away those 6 that were in common, and that's where we get the 32 out of 52 from, which, of course, you can change. You can convert to a decimal. How about D and E? 5 and a queen. Well, that can't exist, so that's 0. So notice when we do D or E, there is nothing to subtract. It's just the 4 5s and the 4 queens. That's 8 out of 52. E or B. So that's an interesting one because E is the event that it's queen. I reversed these. Sorry about that. I put the B first. This is B. B is the event that it's a face card. And then E is the event that it's queen. But here's the thing. All 4 of those queens were also counted in the face card. Which is probably why I put that one first. So you need to take that away. And it ends up being just the 12 out of the 52. The same probability as choosing a face card. A and C, spade and red. Well, spades are black, so they can't be red. So that's 0. So again, when you do A or C, there's nothing to subtract. So let's take this away from the card scenario for a second and do one last problem. I'd like you to hit pause. I want you to read it, and I want you to try the problem on your own, and then come back for the answers. So most of these are given to you in the problem. The first thing we're asking for is, hey, what's the probability of event F? That is the event the person is female. That's given to you. 51.6% of U.S. adults are female, so the probability of females, 0.516. When we cite it as a probability, we get rid of the percent. So what's a probability of someone being divorced? Well, 10.4%. These are really old numbers, by the way, probably from, I think, 2011. 0.104. What's the probability of being female and divorced? Well, there it is. 6% are divorced females. So you have a 0.06 chance of being both divorced and female. So now we do the probability of female or divorced. Well, that's going to come from the formula. This is where we need to take probability of F. Well, that was 0.516. Add it to the probability of being divorced. But then take away that overlap of those females that are divorced, that 0.06 overlap, and you are going to get 0.559. Okay, probability of being male, this is where you're going to get, this is the complementary rule, 1 minus 0.516, which of course is 0.484. Okay, so that concludes our first half of chapter 4, going through some of the basic rules of probability.